So let's try to give an overview of the graphical user interface for the ViDES, which you can download from the website. In particular, if you go to utilities, there are right now two utilities that you can use. One is for making the post-processing of the data, as well as for the graphical user interface, which actually is an IDE. And you can download the code which has been released for a Linux 64-bit operating system. So it's a compiled version, and you need to download you get the compiled version of the IDE, and you have to follow the instructions, and in particular send an email to this email address, specifying the information that you need, and in particular the MAC address of the machine from where you are running the code. And pay attention that you don't have a firewall on, or at least pay attention to have the port 9999 open in order to get access to the code. So supposing that you have correctly downloaded and installed the code, from the command line you can run the IDE, and then you will have an image like this, where actually the IDE is like clearly an editor from where you can open, save, and save as the file with the name that you would like, as well as you have a menu concerned with the edit, where you can copy, paste, cut, and find, and do whatever editing within a Python script. Plus, if the bug has been previously installed, as seen and specified in the instruction that you can find in the website, you can even debug the script that you have developed. But let's here focus mainly on this menu, in particular, and devices and the plot menu. So if you look at the device menu, you see that there are different numbers of devices which has already been developed, and you can find here where you can actually have a template for the device that you want simulate. In particular, you can see that you have different graphene based FETs, like bilayer graphene or graphene FETs, as well as graphene tunnel FET, for which you can compute the output as well as the input IV characteristics, as well as the different carbon nanotubes and graphene nanoribbons, both with ohmic as well as Schottky contacts. And you can even simulate within the FET mass approximation transition metal dechalcogenide FETs. So let's suppose that you wanna simulate, for example, a graphene FETs. Then you go and you select this option, and you'll see that you will have these structures which is defined. So you have different fields that you can fill, and each field corresponds to the quantities which are shown here in the picture. And so you can, for example, change the length of the bottom gate, as well as the one of the top gate, which correspond to LG1 and LG2, and you can change the spacer, and you can change the oxide thickness, the top and the bottom, as well as the different electric constant at the source and the drain molar fraction that you can find here. Here instead you have the IV parameters, where you can choose if you wanna sweep, for example, the bottom gate fixing the top gate, or you can do the opposite, as well as you can decide if you wanna sweep both. And here you can define the range where the gate voltage is varying, as well as the step. And here as well, you can change the source and the drain. You can specify the source, the drain voltage that you applied, since this is actually an IV characteristic. So you sweep the VG and you take then you fix the VDS. You can also make a specify if you want to do it in parallel or not, and if you can even start from an initial solution given in an external file. So if you press, for example, this button, then the script is created, and actually this is the script that corresponds to the structure that you have defined here. And then you can run the script, for example, here. If you want to do on a single core, you can do run with the MPI, given that you have specified the cores where you want to run the simulations. So once you have all the results, which actually by default are stored in the -dati out directory, which is created by the script, then you can think of making a post processing of your data, like for example, and then you can use the plot menu, which is given here in the IDE. So the thing that you have to do is to load the grid X and grid Y, which are stored for example here, as you can see, in the grid X and grid out, grid X.out and grid Y.out files. And so you have to first install this value, and so you go here and you you upload the grid X, and you do the same with the grid out file, grid Y. Okay, and then you can decide which file you wanna download and you wanna upload. And for example, let's suppose that I have the data here, and let's suppose that I want to plot the electrostatic potential. And so now that everything has been loaded, then I can go for plot 2D function, because actually this structure and the domain that I'm studying is a two-dimensional domain. In the case, for example, of the carbon nanotubes or graphene nanoribbon, that I should have gone for a 3D. So let's go for the plot 2D, and I can go and I press the bottom, plot 2D, and here you get the profile, for example, the potential, which somehow I can rotate, and then I can even look at the color map, and I can specify, for example, if I wanna extract a cut of the potential on the X direction, then for example, if I wanna extract the potential on this direction, X, and correspond the X coordinate equal to 0, then I do this, and here I got the potential in this direction. Let's suppose that now I want to do a cut here in the middle, like corresponds to 25, for example, nanometer here along the Y direction. Then I do this like this, and I got this structure. and these results.